So let's get it started. Right, just like a quick overview on the announcement that I sent to you yesterday. So yesterday I sent to you like an announcement, and you should have received 2 announcements. The announcement is concerned about the learning exercises and also the recorded lecture of yesterday. So you basically will go to week 1 and day Monday. You will find our lecture in this tab, rectilinear particle motion. And here you will find the key questions that you should have, the reading from Hippler textbook, or if you want to watch other videos, so you will find it here. And I might add the videos from Dr. Dan Baker YouTube channel. So it's a good YouTube channel to watch it and learning dynamics from. And here's our recorded lecture from yesterday. And here you will find some supplemental links for videos that you might want to watch, or practice problems. So you might click on any of these practice problems, and if you are done with the lecture notes and solved some problems from Hippler, you might check these practice problems. So this from modules, and if we went back to modules, so you will find 2 learning exercise. One of them is getting to know each other, because I want to know all of your names. So you might like put your names, your fun facts, and all of these things in this learning exercise. I think they are 8 questions. And here's another like 2 question exercise on what you learned from yesterday lecture. And also I uploaded homework 1, which will be due to Friday, and we will be covering the last topic of homework 1 today. So you are good like to start solving homework 1 starting today. And this for the modules, and the next lecture, which will be today's lecture, will be uploaded on Tuesday, and we will be having all the contents one by one and day by day in the modules in terms of the week and the days within each week, and the materials corresponding to each day. And for also the lecture is recorded using the Echo 360. So you might like go to Echo and check the lecture. So I don't know how this panel look like. So right now we have one recorded lecture, and this is the second one, which is live right now. I don't know what is the best for you, but both are the same recording, same thing. So if you are comfortable with Echo 360, you go with Echo 360. And if you like the YouTube more, so you might watch the YouTube playlist. So both of them are organized in terms of like a playlist. And here, if you go to my YouTube channel, and you will find our class here, CIVE261. And you can open the first lecture here, and I will be adding our lectures one by one as we are moving forward with our class. So this is a quick overview. So let's get back to Canvas. Okay. So let's get back to our lecture 2. And so the last lecture, we talked about important differential relationships. So we talked about the differential relationship, which identifies V as the time rate of a change of the particle position. So this was our differential relationship. This is our verse 1. And our second differential relationship is that the acceleration is the time rate of change of the velocity. So this is the two important differential relationship in that section of that chapter. So you might also like want to get a relationship between A and V and S. So we can do this using like if you noticed here, we have dt and we have dt here. So from this equation, dt will be equal ds over v. And from this equation, you will have dt will be equal dv over a. And taking these two equations, and both of them should be equal each other, so it will give you that ds over v will be equal to dv over a. So we might get another differential relationship out of these. So you might like say that a ds will be equal v dv. So this is the third differential relationship that we have. So this is 1, this is 2, this is 3. So this is the important three differential relationship between velocity and position, acceleration and velocity, position and acceleration, position and velocity. Also, you can get this relationship by using the differential chain rule. So A will be equal dv, and here will be dt. So this is the same thing, but we will add here ds and ds. So this should be equal this relationship. So this should be equal to that. And you will get the same thing. So this will be equal ds dt is equal to v. So you will have v here, and here you will have dv ds, and you will end up with a ds will be equal v dv, which is the same one here. So both of them should be like give you the same thing. So this is the important three differential relationship. Also, you might want to go backward, like you might like given the position and you want the velocity, so you will use this differential relationship. But if you are given the velocity and you want the displacement, so you might use the integration relationship. So let's show how we can integrate these. All right, so let's pick this color. So number one, v equal ds dt, so ds will be equal to v dt. So if you integrate this relationship from time t node up to t, sorry, this is ds, so it will be s node up to s, and here we will have t node up to t. So this is the integration relationship if we want to get the position out of the velocity. And this will give us this relationship. So if you integrate ds, it will give you s, and if you put the upper and lower limit of the integration, so it will give you s minus s node will be equal to the integration from t node to t v dt. So I didn't integrate v with respect to t because I might put vt, but might be the velocity is function of t, so it is not constant. If the velocity is constant, I can say that this will be equal vt minus t node. This is just in a special case if the v is constant. But if v is variable with time, like v is equal t cubed minus t squared, so I can't do this. I should integrate this with respect to t. So let's delete this. So we might want to put this general. And I would like to mention that, as you know from the integration property, dt could be an x-axis for the curve, and v could be a y-axis. And if we have, this is the relationship between velocity and time, and you want to get s minus s node, so here's t node, and here's t. If you get the area under the vt curve between T node up to T will give you S minus S node. So this relationship should give you the area under this curve. And the second relationship that we have is that, let's move to the acceleration. So will be dv equal a dt. So this is coming from this one. And if we integrate this relationship here from v node up to v, and here from t node up to t, so this will give you v minus v node. And the integration here, we will keep it because we don't know if the acceleration is changing over the time or not. So if the acceleration is constant, you might say it's equal at, but we will keep it as it is t node up to t, and here is a dt. And similarly, if the a is constant, it will give you at minus t node. But we will assume it is not constant for now. And similarly, you will have here, if you have the t on the x-axis and the acceleration on the y-axis, and you have the relationship between the acceleration and time, if you get the area under this curve from t node up to t, it should give you this area. So it should be like v minus v node will be equal to this area. Let's go to the third relationship, which is ADS, which is this one. So ADS is equal to V dV. If we integrated this from S node up to S and from V node up to V, so this will give you, so we can integrate V right now. It will be V square over 2. So this term will be, let's get half outside, it will be V square. And if we substitute with the upper and lower bound of the integration, it will give you V square minus V node square. And this will be equal the integration from S node to SA ds. So this is the third relationship, and I kept the integration form of each one because we don't know if the V is constant or the A is constant or the A here is constant. So, and similarly, you can have a curve with S because here's the ADS, so it should be S on the x-axis and acceleration on the y-axis, and it might be you have like, here's the relationship. And if you have the S node here and S here, if you get the area under the AS curve, it should give you this relationship, and you might end up with the value of the half V square minus V node square. So this is the most important differential and integral relationship. So let's get to a special case. If the acceleration is constant, what will happen? Constant acceleration. So if the acceleration is constant, so let's get to number 2 first here. If A is constant, so we can get it outside the integration. So let's start number 1. Okay, let's start by number 2. Yeah, this one. And you will end up with that V minus V node will be equal to A constant. And here you will have T minus T node because it will be only dt. And if you integrated dt, it will give you T. And substituting by the upper and lower bound of the integration, it will give you T minus T node. So this is the first one, and you will finally can have V as a function of T, so it will be equal to V node plus AC in T minus T node. So the constant acceleration will give you a V as a function of T, so V is not constant, so V is a variable with T. And let's have the third one. which is this one. If a is constant, we can get a outside the integration. So you will have half v square minus v naught square will be equal to a, which is constant, and here it will be, you will have ac multiplied by s minus s naught. So this is, we can get this from here. So let's get to the verse 1 because we have v inside the integration, and from this rule you can see that v is function of t, so we need to integrate this. So here we will have s minus s naught equal to the integration t naught up to t, and v will be equal v naught plus ac t minus t naught. And all of this is integrated with respect to dt. So let's integrate this relationship. So finally it will give you v, so this is v naught, which is a constant value, so it will be v naught t plus, and here you have t inside, so this will be square, and you will finally end up with half ac t minus t naught square. So this is the most important rule. So we have the basic one, the differential one that has va, and here we have a as a function of v. And then we have another 3 that here, let's name it non-constant acceleration or velocity. So they are function of time. And special case of the, if we have a constant acceleration, so we will end up with these rules. So you should be able to get this by doing your own integration, so you will able to deduce these relationship. However, I have here on the canvas, you will find the modules, and I think I published the modules, and if you go down after all these materials, you will be able to find a sheet that has all of the equations that you should be able to use during this class. So you will find the practice problems here, all of them are published. Yep, and here you will find the dynamic full equation sheet. So for the dynamic full equation sheet, yeah, so you'll find all of these equations here. You will find the general equations, VA, and also you will find the non-constant V or A, S minus S node, and you will find the one for the constant A. So you can you don't have to deduce them from versed principle. You just can use the direct equations without using the integration and differentiation. And also you will find other equations that we will be moving forward with the Cartesian coordinate system and tangent normal. So you will be able to find all the equations, almost all of the equations that we will be using throughout the semester. So yeah, so let's get back. So you are allowed to use this sheet. So it's a 2-page. I would recommend that you print both of them and have them with you while you are in the quiz or doing your homework. So it will allows you better to, you don't have to memorize these equations. So you can just directly use them. And if you want to consume some time of your quiz time and deduce them, but I don't recommend this. Just even memorizing them or use the sheet directly. All right, so let's see a direct example. Yeah, just like one thing I would like to mention very quick, and you should know this, that V, as it's V equal ds dt, so we can say that V is equal to S dot. So the dot represent over any letter represent dt of this letter. So if you have s, so the dot means the rate of a change with respect to time. So v will be equal to s dot, and you can also do the same with a. A will be equal to v dot, because v is differentiated with respect to t, or it could be used as s double dot. So s double dot means if you have anything, so double dot means d square dt square of this thing. So this is for now. All right, so let's get some a small example. So if we have a relationship between S and T and another one, and we need to get the V with respect to T and also the A with respect to T. So if the relationship between S and T is a parabolic curve from the second degree, like it's like something T square, and we want to get the relationship between V and T and A and T and want to know how it looks like. So let's see how this look like. So as we know that the V is equal ds dt. So it's the slope of this curve at any point. So as you can see, while S increases, T increases. So here's the ds, and here is dt, and here's the line. But the slope of this line is getting decreased as we move until it gets zero here. So the slope is getting decreased until it hits zero, and then get negative, because as time decreased, as time increased, like here's dt, ds will get increased. So the slope is getting decreased. So this could be like, so if this is a second degree, like is a function of t square, so the v with respect to t will be a linear. So the line will start at some point, which is the slope here, and we'll end up with at here will be at this, like let's say that this is t1, the slope here is 0. So if it starts here, it will end at 0, and then the other part will be negative, and it will be on the same line because it's a continuous function. So this is how the VT relationship will be look like. So if the V with respect to T is linear, so the A with respect to T will be constant, because A equal to dV dt. If you differentiate a first degree curve that's function of T, will give you a constant. So, but we don't know, like for now, what is the constant value? Is it positive or is it negative? But you can know from the slope of this curve. The slope of this curve is negative as time increased in this direction, the velocity get decreased. So we know it's negative, so it should be something here, and this is will be A will be constant, like something like this. So this is the value of A. So this is just show how the degree, like let's say that S will be equal 5t squared minus 2t. So let's get V. The V will be equal, if you differentiate this, it will give you 10t minus 2. So it turns from second degree to first degree. And if you differentiate V with respect to t another time, will give you A, which will give you 10, which is the constant. So this is how the degree of the equations are getting decreased while we are doing some derivatives to go from the displacement to velocity and then to acceleration. All right, so let's solve an example and see how this look like in terms of an example. So let's get here. All right, so this example says that here is the origin that the car starts from, and here's the car. It has an acceleration and velocity, and as we can see here, the velocity is function of t, so it's not constant. And also you can like simply imply that the acceleration is also not constant, because if you differentiate this relationship, it will still be function of t. So a and v is not constant. So it says that the left car in the photo moves on a straight line, so we know it's rectilinear motion, such that for a short time its velocity is defined by this relationship, where t is in second, determine the position and the acceleration when t is 3 seconds. So, so as we have v, like here's the v, equal to 3t squared plus 2t, we need to integrate this relationship to get the position, and we need to differentiate this relationship to get the acceleration. So we know that from above there, if we go up there, so you will find that s minus s node is the integral of the v dt. And here's it says when t equals 0, so it gives you the initial condition of this car, the s equals 0. So it means that the car started from at rest from O, and start from rest, because if you substitute by time 0, t0 in this equation, so it will give you 0. So it start from rest and from origin 0 here at time 0. So s minus s node is equal to the integral from t node up to t v dt. So we know that s node is equal to 0 because the time t node is equal to 0. So here's 0. So s will be equal to the integral from 0 up to t, and let's have 3t squared plus 2t dt. And if you integrate this relationship, it will give you t cubed plus t squared. And if we want to get the displacement s at 3 seconds, which is required here, t equals 3, so you will basically will be equal 3 cubed plus 3 square. If you solve it, this should give you 36 foot. Because I put the unit foot here, because if you noticed over there, the velocity is in feet per second. So all our units is feet or second. So this is the position at t equal 3 seconds. All right, so let's get to A, which is much more easier. So A will be equal to dv dt. So if you differentiate this relationship, it will give you 6t plus 2. If you want to get A at 3 seconds, will be 6 multiplied by 3, which is 18, plus 2 should give you 20 feet per second square. So this is the solution for this problem. So we got all what he wants, the position and acceleration at t equals 3 seconds. So what if we added more difficulty to this problem? Like, what if the v is not like this? So let's get this function. If v is equal to 3t squared minus 6t. So let's copy this. So if v equal to 3t squared minus 6t. So here it will be more complex. It says if it's initially located at the origin O, determine the distance traveled after 3.5 seconds and the particle average velocity and average speed. So let's differentiate between these two during this time interval. So here in this problem, I said it's complicated because if we draw the VT relationship, and if you substitute in this relationship with, if you substitute in this relationship with t equals 0, it will give you v will be equal to 0. If you substitute, let's here v0 will be equal to 0, and v1 second, if you substitute here by 1 second, will give you 3 minus 6. It will be negative 3. And at v equal 2, it will give you 3 multiplied by 4, 12 minus 12 will be 0. And v at, let's put 3.5 second, it will give you, if you substitute in this relationship, 15.57. So just like direct substitution. If you draw the relationship, and here at 1 second, it will give you negative 3, like this. And at 2, it will go to 0. And then at 1, 2, and here 3.5, it will give you 15.57 meter per second. So here's its meter per second. So this is how is the velocity changing. It goes into the negative if you have like, and here's the origin, and your car started from here, the car will go to the negative, I mean like this way, and at this time, it will change its direction and then go there. That means if we are going to calculate the average speed, so here we need to find the total travel distance. So we need to find this and this and then this until it gets here. So let's see how we get the total travel distance. And so here we have v equal to 3t squared minus 6t. If you want to get s, so s minus s node will be the integration from t node up to t. And it says it's initially started at the origin. All right, so 3t squared minus 6t dt. So let's integrate this. And we have s node equal to 0, and t node will be equal to 0, and you will end up with s will be equal to t cubed minus 6t squared over 2, which will give you 3t squared. And if you want to get the distance at each one of these steps, so let's do the same. S at t equals 0 will be 0. S at t equal 1 should give you 1 minus 3, which will be negative 2 meter. And s at t equal 2 should be t cubed minus 3 t squared, 2 squared. So this should be a negative 4 meter. And s at, so we know that t, so here's the change in the velocity is going positive. So and t equal to 3.5. So it will be 3.5 cube minus 3 to 3.5 cube. So this should be equal to 6.125 meter. So let's see how this will look like. Let's draw this here. And here, let's say that this is S and this is the origin O. Let's say how this will look like. So at t equals 0, so the particle was here, and then it make -2 at t1 second, and then -4. So here it goes -4 at t equal 2 second, and then it came here at t equal 3.5 second and made a distance. Okay, let's -4, came here back 6.125 meter. Okay, so we know how is the distance look like. So the particle average velocity. Let's get the average velocity. So V average, as we know from the last time, it's equal to delta S, the total, the delta S between the final minus the initial over the total time delta T. So let's see what is the total distance that this car did. Like first, it came here -4 and then made another +4 and then made another +6.125. So this is the total distance between the particle at T0 and T3.5. So this is delta S. So delta S will be equal 6.125 over delta T, which is 3.5 second. If you calculate this, it will give you a 1.75 meter per second. Let's get this is the average velocity, this one. Let's get the average speed. So for the average speed, V speed average equal to S traveled over delta T. So S traveled, this particle made a 4 and another 4, so 4 plus 4, and another 6.125 over 3.5 second. So this will give you 4.035 meter per second. So this is the average speed of this car during this interval. So how I can distinguish in my problem that I should go through all of these steps rather than do it simple like this car. So it's basically, you can notice that all the t values are positive. So it's never that the velocity will be, because the time will never be negative. It's always positive. So the velocity will be always positive. So you have here 3t squared positive, and also 2t is positive, so the velocity will be positive. But here you have 3t squared positive, but minus 6t is negative. That means maybe at some point this particle will have negative velocity, so I will have to check, and this we call erratic motion. Erratic motion. That means that the particle goes backward and then goes forward and keep moving forward. So this is the differences. All right, so anybody have any questions until now, like any issues, didn't understand anything, want more clarification on any of these things before I move forward? Nobody have any questions? All right. Okay, so let's see another example on how the erratic motion look like, which is chapter like something similar to this one. If we say we have here example. Okay, let's pick this one. So this is another example of the erratic motion, the motion that are defined by two separate functions. Like this example says that this bicycle moves along a straight road. So straight roads means that we will be using rectilinear motion such that its position is described by this graph. So the displacement over the time in the first 10 seconds is described by S equal t squared. But after 10 seconds up to 30 seconds, the displacement is described by this linear function 20t minus 100. So how to solve this? It asks us to construct the VT and also the AT. So similar to this curve, we will be having two separate functions describe the V over the time, and also another one describe the acceleration over the time. So for these problems, you will have to separate your solutions. So you will have your answer for time t more than 0 and less than 10 seconds. And let's solve this problem. So you have S equal to t squared. So V will be equal to ds dt, which will be equal to 2t. And if you substitute at v equals 0, I mean like time t equals 0, so this will be equal to 0. And v at t equal 10 seconds, which is this one, so it will give you 20. And it should be this in foot, so it will be foot per second here. And let's get the acceleration. So A is equal to dv dt, so it will be equal to, so it's constant. And let's get to the second interval for t is more than 10 and less than 30. So this will be equal, like the position is equal to 20t minus 100, and if you get v, so if you differentiate this, it will give you 20, which is constant feet per second, and this, do not forget the units, feet per second square. And the acceleration is dv dt. So if you differentiate the constant, will give you 0. So the acceleration, there is no acceleration. So the constant velocity ended up with a 0 acceleration. So let's draw the graphs for time in seconds and velocity feet per second. Okay, so we have two relationships separated at time 10 seconds and the end of motion at 30 seconds. So let's draw the first one here, 2t. V at t equals 0 will be equal to 0, and V at 10 will be equal to 20 feet per second. So let's say that this is 20 feet per second, and it's linear function, so it will be line. And after 10 seconds, so we should use this equation. So it's constant, it's 20. So I start from here and end up here. So this is how the V with respect to t look like. So it has a linear function from 0 to 10 and then constant from 10 up to 30. And let's get to the second one, which is t in seconds and the acceleration in feet and square. All right, so from 0 to 10, we will be using this function, which is equal to constant 2. So let's have it here at 10 and then 30. And let's draw the curve. So it will be equal constant, and here's 2, positive. And from 10 to 30 is equal to 0. So here it will be 0. So we only have acceleration only in this interval. So this is how is the velocity and how's the acceleration look like for this erratic motion that has two functions that describe the position with respect to t. So does anybody have any question on this problem or anything else during this lecture before we move forward with the some class exercise? All right, so let's get the class exercise here, the one from yesterday. And let's have this verse 1. Copy. And let's put it here. Best. And let's make it bigger. All right, so I want to make a multiple choice. And anonymous. All Let's add this question. So, I don't know. Okay. I think I might have created this before. Okay, no problem. All right, so this was the versed question of the lecture exercise from yesterday, and you were asked which one of the following figures represent a particle moving with increasing speed. So if you know the answer of this question, you can raise your hand or whatever. So does anybody know the answer of this question?
Wouldn't it be A because it's nonlinear?
Yeah, exactly. So the right answer is A, because for the B, if this is an S with respect to t, which is constant, if you differentiate this constant, it will give you 0 velocity and 0 acceleration. Similarly, S with respect to t is linear, so it will give you constant velocity but 0 acceleration. And also D is linear, so it will give you V equal constant and also A will be equal to 0. So this is the only one that is curved and will have a linear velocity. So V is not constant, it's linear. So it will be a function of t, or whatever. It could be more like second degree or third degree, depends on the degree of this curve. And A, it will never moves with increasing speed because the slope is getting increased. So it will be A. All right, so let's go to the second question. So for this question, it asks for, in all of the following figures, the magnitude of the acceleration vanishes. So except. So does anybody know the answer of this question? Yeah, go ahead if you know.
Would that be B?
Yes, exactly. So yeah, for V and T, it's a constant velocity, so it will give you 0 acceleration. And for C, it's X over T is linear, so it will give you a constant velocity. And A will be equal to 0 because the derivative of the constant will be 0. And here's the same, it's still linear. So the right one is B because it's a curved relationship between V and T, and the acceleration will not vanish. All right, so let's get the second one, the third one. So for the third one, it asks us which of the following figures represent a particle moving with uniform deceleration. So just be cautious about acceleration and deceleration. So does anybody know the answer of this question?
Wouldn't this one also be C?
Yeah, exactly. So for A, V is equal to 0. So it means like the acceleration will be equal to 0. And here is not 0, but it's a still constant. So if you get the derivative of this, it will give you A equal to 0. And for D, it has an acceleration, and it's a constant like uniform acceleration, but it's acceleration, not deceleration. The body is increasing its speed over the time. So, but here, so this is a positive slope, but this is a negative slope. So this body is decreasing the acceleration over the time, the speed over the time. So it starts from here and keep decreasing the speed until it gets to 0 at this time. All right, so let's get the last one. So for this one, it asks us about the opposite figure represent a velocity-time relationship, which is the following is true. So the body is always accelerated. The body is, it changes direction of its motion after 2 seconds. The body stopped instantaneously at 2 seconds. The body moves by uniform acceleration. So does anybody know the answer for this question? Which one of these is true?
Well, C would be true, wouldn't it?
Exactly. Yeah, that's right. So let's get it them one by one. So the body always accelerated. No, it's not, because from 4 to 2, the velocity is decelerated, and after 2, the velocity is accelerate. I mean, like it's increasing, so it means it's accelerating. And B, the body changes direction. So the change in direction means that like you are here and your body's there and its move was positive and then at some point have negative velocity. So here at the two intervals, the velocity is positive. Like from 4 to 2, you didn't hit any negative here. So there's no changing in direction. And the fourth one, the body moves by uniform acceleration. It's not, because we don't know the function of this curve, if it's t square or t whatever the function is. So we don't know if it's constant or not, and it is not uniform because it decelerate and then accelerate. But what we know, the body stopped instantly at 2 because the slope here is 0. So it keeps decreasing, the velocity keep decreasing until it gets to 0, and then increased in its magnitude. So this is the solution for the 4 question from yesterday exercise. And I think with this, you will be good to go to solve this homework problem. The homework one, which will be due to Friday, June 18th. So I will be posting the homework solution. Just do your best in this homework. I will be grading this homework based on the effort, not on the right answer. And also I will be providing the final answer for each problem. I mean, like the number, not the steps. So you should like follow your steps and get your final answer. And after you get your final answer, check the one with the one that I provided you with. And if it doesn't the same, just try your best and see like until you get the right answer and discover your math error. Sometimes like when you solve the problems, you change the signs from positive to negative, you forget to do squares, you do any sloppy math error. So just like be focused and be systematic, because the mechanics and the dynamics and statics and all of these branches have a lot of mathematical calculations with a lot of signs and a lot of squares. So you will have to be cautious while you are solving the problems, and don't get distracted when we are dealing with numbers, because just like one sign will give you different answer. So you will be good to solve homework 1, and I will be posting the lecture recording for the students who didn't attend today. And I also will be post the learning exercise that you are supposed to, because after every lecture we will be having new learning exercise. It's just like few multiple choice questions, and the due date for them is like 1 or 2 days. So it shouldn't take like more than 5 minutes or 10 minutes to solve this learning exercise. And also homework 1, I would recommend just right now, if you have some time, go through the notes and then start solving this homework. And you might check Kepler textbook for if you like miss anything. You might check any other online materials until you are good to go and solve the homework. And then if you have some other time, you might check the Kepler solved example, the Kepler non-solved examples, and also you will have some practice problems for each class if you get there, and you will find the practice problems at the end of each module. So with this, see you next lecture if anybody doesn't have any question.
Thank you, Professor.
Thank you.
Thank you.
Thanks, and see you tomorrow.
Yeah.